think that's the best exercise of anything I can think of.
Whatever, work out what
I heard you were, where you had? I want to see this.
I already separated you.
I have to stand in line. Apparently, I'm an instant celebrity with my relationship to my third chicken. So, anyway, next Thursday we'll hear from Jason Shankle. There's been essentially a picture in our welcome presentations. He's going to talk about, I'm sure, the same thing, SPORE, and that's next week. This week I have the immense pleasure to introduce to you Wendy Bartlett of Hewlett Packard. And from where I come from, frontiers were wild. She's going to tell us about fault finding. So let's welcome her.
So this talk is going to be a mix of technology and sociology, and I'm happy to field questions all the way through, so drive it whatever way is of interest to you. This is what happens when you work for a big company. People spend millions of dollars producing standard slide templates that look like this, so it does calm down after that. So the things that I'm going to cover in the course of this is something about the nonstop architecture and what made it unique at the time and why it's still somewhat unique. You could say Tandem was a success disaster, and the reason I say that is that two weird things happen when you're wildly successful. The first is that you start growing like crazy, which means that the company starts growing like crazy, which means that you had 50 people in development this year, and you've got 100 next year, and you've got to figure out how to get everybody assimilated and trained working together. And the other part of success disaster, at least in the end of the business that we're in, which we tend to call mission critical computing, is that your customers have expectations that are like up here. And so when you bring out a new release, it's not okay that, oh, we decided we had a really better way to do the GUI for this, so we changed all the commands. Surprise, you could retrain all your operations staff. Or, oh, I really don't like what that function call looks like, so we redesigned the whole thing so you can improve your apps. That kind of stuff just doesn't fly in the part of the market that we're in. Highly sensitive to it, so you wind up, kind of the chains of what you did yesterday with you for the rest of your life, and in 35 years we've accumulated a lot of chains. When I started at Tandem, I was about the 35th person in the development, and we were about a 500-person company. I now work for HP, which is in the process of digesting EDS and is a 200,000-plus person company. It's different. Yeah?
So, I'm a little bit obtuse here, but Tandem was bought by Compaq. And so Tandem's still surviving, thriving?
Yeah, basically, we started Tandem in '74. We shipped our first system in about a year and a half, and something like 10 software developers, maybe fewer, did all the work to produce a fully functional system that went out the door. So that was pretty amazing. And we did one of these startup things where you're a wild success, you go like this, and then you start hitting the bumps in the road, and you sort of start going like this. So we kind of rocketed up to being a $1 billion company, and then we sort of bounced our way towards $2 billion and kind of flattened out. And one of the other things that you see in startups is that when they get big, they need different skills to run them than you do when you're running a 500-person company. And so one of the things that happened to us a little before Compaq bought us was that we got a new CEO brought in from the outside. And the joke, at least in my neck of the woods, was that he was hired to dress us up and sell us, and he succeeded in doing that, and Compaq bought us. I still really don't know why on earth they bought us. The only thing I can think of is that they were really driving to be a $50 billion company, and that they wanted to get some higher margin business, and so they could pick up a quick $2 billion by getting us. And so they got us, personal opinion, they just about wrecked us in the process because they totally didn't understand the sales model of these systems. We're talking multi-million-dollar systems, long sales cycle, really hands-on working relationship with our customers. We understand their business problems, we understand what they're trying to do with their applications. Compact model is more how many truckloads of PCs can you sell, which is not either a long sales cycle normally or something that takes a whole lot of kind of value add in understanding your customer. So they bought us. Most of our top salespeople walked out the door in the first year because they didn't understand the difference between high margin and high volume. It's why it was taking so long to bring sales in. And then Compaq turned around to me, they're like really interesting and bought digital equipment. Now, digital was another interesting story. My husband was one of the guys, first software people at Tandem, and left in '86, went to digital because he wanted to go work in research. And he sort of landed on the crest of that wave, and then digital started sort of dribbling down. And I think digital was still bigger in terms of number of employees when Compaq acquired them than Compaq was. So even though this was an acquisition, officially it was really kind of a merger because it's awfully, there's that old saying, don't eat anything bigger than your head, and that's what Compaq was trying to do and digest. And so we all sort of lived through that, and then Compaq and HP merged in 2002, which from my point of view made a fair amount of sense, because if you look at where the two companies were strong, it was not necessarily in the same product line, so they were able to actually pick and choose and say, we're going to take the Unix from here, we're going to take the Intel servers from this company, and so forth. And it was a lot better planned. So it's different. It's just, there's nothing like being in a company where you're all in the same building and the president's down the hall and the head of sales is down the hall, and you've got hardware and software people in the same office. And yeah.
So DEC makes used to make mainframes, or
DEC made mini computers more than anything else. They were one of the first companies that was really successful with the PDP-11 line was the one that they did that really had a lot of legs, and the PDP-10s were the bigger machines. Where DEC missed the boat is that Ken Olsen, who was their CEO, didn't think anything was going to come of this PC stuff. So they just were, and workstations were something else they did, but really, they missed that boat, and they missed some other boats, and paid for it. So I joined Tandem in '78, so I'm dating myself, except that it wasn't my first job, so I'm dating myself even more. But I got hired in basically to do the first thing I was qualified to do, which turned out to be quality assurance for the Fortran compiler. That lasted about 6 months, and I managed to work my way into the OS QA and then into the OS group. I'm software background, but I'm really a systems person, and I've spent a fair amount of time with hardware guys over the course of the last 30 years. I did try management, and this was something that was really cool about Tandem, was that you weren't penalized as you said, I want to try being a manager. Oops, I don't think that was the right choice. I'm going to go back to being a techie. That seems to be a lot harder these days, and so the only advice I have in that for you is if you're thinking about going into management, you might try it earlier rather than later, because it gets harder in the way, especially big companies are structured, it's hard to move back at the same level that you were at before when you go back to the techie world. There are other alternatives. There's programmer project management, which requires techie smarts, but also a lot of dealing with people and dealing with scheduling and making sure that you know what you need to do and the right things happen in the right time. I'm kind of strange for a techie. I don't write code. I haven't written code for 25 years at this point. Because what I discovered is that I'm really good at design, I'm really good at debugging, and I'm an okay programmer, but nothing to write home about, and you can get people who are a lot better at it than me to do it. This isn't true of the majority of the people in my group. Almost everyone else codes. I can think of a couple other senior people that don't. And some of them do it because they feel they need to. Some of them do it because they need coding fixes. And so that's something that really will depend on what your taste is and what your company's willing to tolerate. And so I've been doing system stuff all along, operating systems, system design, balls and arrows stuff. How do the pieces fit together? How could they fit together? How could they fit together differently, and what would be the consequences of that? And in the last few years, I've started doing some work on security strategy as well. But it should be a full-time job, but all my like compatibility stuff, all my old hacks of what I used to do trailed behind me, so I haven't gotten rid of them. It's 1974. Nixon had resigned from office in the last few months. We had our first wonderful gas scare where the Arab gas embargo drove the prices up, and people drove on alternate days. People hung out in lines for hours waiting to get their precious tank of gas. Not a whole lot of fun, and a lot worse than what we've been seeing lately. The financial world was really different, and this is where Tandem comes into the picture. There were just beginning to be ATMs. There weren't a lot of them. They weren't up that reliably. You went to the bank, you talked to the teller. People used checks a whole lot. People used cash a whole lot. They had credit cards that didn't use all that much. So just how money worked was just nothing like it is now. At least in my neck of the woods, there were also a lot of hot tubs getting popular, and parties that wound up with the remaining guests in the hot tub singing at the top of their lungs at midnight. The computer world was different. You kind of worshipped at the throne of the mainframes. IBM was the king of the world with the 360 series and then the 370 series, which is predecessors to the current Z series systems. Bill Gates was at Harvard, he hadn't dropped out yet, and Jobs and Wozniak were meeting at the Homebrew Computer Club. So the real personal computer idea was just kind of beginning to bubble up. Mostly you had mainframes, and then you had people like that selling mini computers. It was a recession. It was hard to compare to where we are right now, but at the end of my junior year, I was a summer intern at IBM. At the end of my senior year, none of the vendors were hiring. So I wanted going to work as an application programmer because I needed a job, and that was what I could get. And spent the next 5 years trying to get my feet back in the system side of the house. There was some venture capital. There weren't a whole lot of venture capital companies. There was nothing like the startup culture and IPOs and all that we've had over the last 20 years or so. We were very lucky for Tandem because the idea came out of some people that worked at HP and then went to what was then Kleiner Perkins. So we had a lead into getting enough money to get going. The other interesting thing about starting a company during a recession was that people were desperate for business, so they would lend you things. So a lot of the equipment we got started on, you know, we got terminals as evaluation units and good deals on leases of computers to do development and so on and so forth. So in a funny way, it was a good climate for a startup. There were no microprocessors to speak of. The first tandem system, we designed our own processor. It was done out of 4-bit TTL arithmetic logic unit and chips and a whole bunch of other stuff, gluing them together. Semiconductor memory was new. It was still considered kind of risky. We actually shipped our first couple systems with magnetic core memory. The big argument between development and marketing was whether the first system was going to go out with 64 or 96K, not meg, of memory. And disk drives were about that big. They looked like, overgrown tortilla holders, and when the things the size of washing machines and had 2.5 meg on them. So the whole scale of life was just way different. Computer vendors did their own thing because that was the environment they were in. There wasn't a whole bunch of stuff out there to leverage. Unix was kind of kicking around in Bell Labs, and IBM had its proprietary stuff, DEC had its proprietary stuff. You built your own hardware, you maybe bought your own disks. You developed your own programming languages, and you wrote your own operating systems. So doing a startup was way different than it is now because there wasn't any free lunch, there wasn't any open source to leverage, it was just do it yourself. So the idea behind Tandem was looking at the commercial market and particularly the financial market, seeing that there was a niche for something that was more reliable than what was out there. And so the idea that the founders came up with was, let's do something that's a single fault tolerance so that it will stay up pretty much regardless of what awful thing happens. And then the other half of it was, we're dealing with financial data, you would really like not to flip this and then otherwise mangle it, so let's really focus on data integrity. And in a way, the environment being what it was at the time let us do that because you're building your own processor, you can build in as much integrity checking as you want. Today, you pick up your Intel chip and you get what you get. And there's no, fundamentally there's no way to get your fingers inside the chip and make things any better if you don't think it's good enough. So that was an opportunity that I think would be harder today in some ways. Markets we were after, things like stock exchanges, banks, Citibank bought us, first customer, and really helped get ATMs up and going, reliable enough that you could depend that if you went over there, you might actually get some money out mode. So I talked about the fault tolerance and the data integrity. The other things, one came along and the other kind of fell out of the design, is that you really needed to be able to repair hardware online. Because if you're going to stay up, you can't say, oops, sorry, I've got to take it down so I can plug into the processor for it. So that was a place where I think we were ahead of an awful lot of companies at that time. And the other thing is, if you're going to stay up for a long time and your business is going to grow, you need more horsepower. What do you do about that? And being able to add horsepower online. So when the original small group, hardware and software, was probably maybe 10 people that started, and that included disk controller, comm controller, processor, interconnect, operating system, compiler, microcode, channel microcode. So it's a pretty busy bunch of people. Modularity was key, both in the hardware and the software. You need it in the hardware for fault containment, you need it in the hardware for, being able to repair something without having to take a bunch of stuff that's working fine out of service in order to do it. If you're going to survive single faults, you need redundancy. You need it both in the software, you need it in the hardware. And the other key piece, and this particularly goes with the data integrity, but it also goes with the availability, is being able to detect that something's wrong and do something about it so it doesn't propagate. And so in either one, the first piece is you've got to detect it. You don't want silent data corruption. The second piece is once you've detected it, what do you do about it? Can you recover? Can you correct? If you can't, you better just stop doing what you're doing. So one of the interesting design characteristics of the system was and is that rather than screw something up that you shouldn't, you should fail something. And this occasionally gets hard to explain to customers who sometimes find it disruptive even to lose a single processor, even though the system is fault tolerant because of, they haven't got the load balance right, or their application's designed in a way that it doesn't handle that very well. But it's really important if you're trying to build something reliable that you can detect and either correct or fail. And that you understand what the characteristics are and you can explain them. So here's a state-of-the-art slideware from 1976. What we had was anywhere from 2 to 16 processors. This is shared nothing, so this is an NMP kind of system. We built our own interconnect. We called it the Dynabus, or it got called the IPB most of the time for interprocessor bus. From a design point of view, this is one of these things that you really need to overbuild because it's got to be absolutely able to handle peak loads without falling on the floor. So if you go through the history of our system, you'll find that's always been the most overbuilt thing in terms of capacity. Individual processors had their Dynabus controllers, IPU, memory, and at this point, one I/O channel, another bus. The fault tolerance for access to hardware comes from dual-path disk controllers, dual-path disks, so that you can build this kind of configuration where, it doesn't matter, you lose one of these guys, you lose one of these guys, lose one of these guys, you can still get to all of your data, or you can still get to the outside world that's calm. What we did with disks was, and still do today, is host-based grade 1 mirroring, which is that you have two shadow copies. You have a disk and you have a shadow, and so you write to both when you write. And if you're really paranoid, you can do one write through one disk controller and the other write through the other controller, so that if there's something bad in the controller, it doesn't get propagated to both halves. So that's what things look like. Yeah.
How do you pick which one's right?
Okay, so how do you pick which one's right for disk data?
Yeah.
Is that we did something different from the start, which is that we formatted our disks with 514 byte sectors instead of 512, and we put a 2-byte checksum on it. So the general model, and it's still true today, is that you write the data to both sides, you read off either side, and that's a nice example of where you have two resources and you're actually making use of both of them, because we can get a lot better read performance by reading off both. You read off it, you compute the checksum. If the checksum is bad, you go read off the other half. If the checksum's bad on the other half as well, then you've got a real problem, which is why you do things like do one right through one disk controller and the other through another. So it's an end-to-end checksum that gets computed up in the CPU and run through everything and check in the CPU and run through everything. And the thing that's been really nice about that moving forward is that we're using more and more commercial off-the-shelf technology in our systems. The newest systems, basically the interconnect is the only thing that's proprietary from us. And so when you're using proprietary stuff, you've got to take the check and you've got with it. You can't add anything in it. So you do things like run end-to-end checksums that let you make sure that even though you've gone through some unreliable stuff on the way, you're still happy with what came out the other end. So that's a piece of technology that's stayed in good stead. Yeah.
When you say that you would do, the way you phrase it is that you would do one write to one controller, another write to another controller, is that something that was up to the application developer to decide, or was that the OS?
Customer system configuration.
Okay.
Basically, what you configure is the paths. And so you configure that, you'd be getting this volume that way and this disk from that side. The design was process and message based. My husband Joel, who did the kernel, had been reading Dijkstra and took Dijkstra and just sort of did what he figured was a kind of natural extension of it. And it's a scale out kind of architecture. What we said at the beginning was 2 to 16 processors in the system, and of course we thought 16 was a huge number and no one would ever get there, and it took about 5 years for the first customer to say this isn't enough, which is longer than it might have been. And then you can cluster the systems together, or you can connect them by wire area network to effectively build a larger system. As I said before, the general model is that you're trying to make all the components do useful work. There are 2 reasons for that. One is you get more bang for your buck, and the other is that you don't have anything unexercised lying around. You really wouldn't want one path to your disk to fail only to find out that the other path is bad as well, and you didn't know because you weren't checking. So in general, we try to use everything, and in a few places where you aren't using everything actively all the time, we'll do periodic probing just to make sure things are alive and speaking to you. Most of the secret sauce, especially these days, is in the software. It's not in the hardware. There was a lot of invention at that time in the hardware, but you look at everyone's systems these days, and you find failover, and you find dual paths, and so on and so forth. The real difference is that we've been designing them in from day one, but the thing that's more of a differentiator now is what we do in the software, which I'll show you a bit about. Each processor is pretty independent. It's running its own copy of the OS for fault isolation, and we always had applications in their own separate address spaces, which cuts down on the ability to have things trashed and not know why they got trashed. In the beginning, it wasn't so true of the kernel processes. They were running in shared address space, and as soon as we could, we fixed that, so that they're largely running in their own spaces, which means you can actually kill them with some trust that the rest of the process is still healthy. So we implemented resources as processes. So if you're going to write to a disk, the disk has a name, and remember this was 1974, so the disk is named something like $data. And so as an application, you open a file on $data and you say write. And inside the system, that gets carried over to a process known as the disk process, which is the process that manages $data. And then it's responsible for actually driving the I/O down to the disk and so forth. So it's, in a weird sense, it's object-oriented. You've got a resource manager for a disk volume, and it's cool in the sense that you don't have things like distributed lock managers because all the lock information's in one place. So what we built, and these days it's mostly used as building blocks in lower levels of the system more than in applications, is process pairs, with the notion that one process is doing the work and all the message traffic gets directed to it and it's checkpointing enough state to the other side that it will be able to take over in mid-flight without having to abort transactions and things like that. And so this is, in a way it's a form of virtualization. You say, I want to open this file, you don't care what processor or what process the disk process actually is at any point in time. You just say, go find it for me, which is where the routing abstraction kicks in. And there is a little bit of global data like this routing data of, if I say I want to open dollar data, where the heck is this process that is kept as a copy of the state in each processor, and we've got algorithms for replicating that reliably. So the trick with process pairs is to know what to checkpoint and when to checkpoint it, because your performance is going to stink if you checkpoint everything all the time. And on the other hand, you have to make sure that you've got the right state on the other side and that it can find a clean takeover point if it should have to take over. So it's really kind of an art form, and there are some people that are very good at it, and after we got some experience with it, we decided that while we've told customers how to write these, we prefer that they didn't have to do it themselves. So what we wound up developing was an application server management infrastructure that you basically configure. I want this many copies of this application running, and you can dynamically add X more if the load gets higher and spread them among these CPUs. And the infrastructure is responsible for starting them and stopping them and replacing them when they die. And they handle data integrity by using transactions. So by and large, our customers don't write process pairs, and well, they're off for it. The thing that checkpointing process pairs protect you from is non-deterministic failures. If something gets timing related, gets screwed up in the state of one process, and you're not going to have the same environment when the other process takes over. And we've done some studies on it. They actually work most of the time. What they don't help you with is the deterministic kinds of problems where you're going to reliably get a bad address trapped if you do this calculation, and then you just retry it to the other side, and it reliably does the same bad address calculation and traps. So we do see double failures occasionally, but we don't see a lot of them. Partly because we beat them out of it before it ever gets out to customers. We don't spend much time on that. So what was ahead of its time was the process and message structure, the kind of semi-virtualization of resources that you address with my name as opposed to by this process and this CPU. All the dual pathing. We had ECC on memory way back before most people were doing that. One of the interesting repair aspects was the ability to hot plug a board back onto a bus and not have the bus go nuts. So that was another area. And dual power and dual fans, because you didn't want to lose something just because the power supply or fan got sick. So what's changed in 35 years? The really big things that have changed on us are the processors, the instruction sets, interconnect, and then, just the whole scale of going from 64K to 16 gigabytes. It tells you something about the change in horsepower. From a technical point of view, aside from just dealing with new technology, the big things for us have been application level compatibility and network level interoperability, because most of our customers have multiple systems. And this is the bottom line from our customers. These are the people you're doing this for. We've had people be able to pull a program object off a tape and put it on a system 10 years later and run it. It runs. But that's the kind of environment we're in. It's way different from the, oh, I think I'll change this release because I know how to make it better environment. And, what you run into is just going to depend on what kind of business you're in. But minor compatibility is good. Recompiling required is already really bad because some of them have 25 years of applications and millions of lines of code, and they don't want to, even if they can find it all, they don't want to go in and change it all. So, and that's where recoding is even worse. And we did this last one once. We'll never do this again. We made a change that required everything that was on the high-speed interconnect to be rebooted at the same time. And our customers told us in no uncertain terms what they thought of that. So it doesn't happen anymore. Big technical challenge if you're a systems person. And sexy's in the eye of the beholder, but for most people, infrastructure just isn't sassy. It's hard to sell compared to new features. It's hard to sell compared to more performance. It's hard to sell compared to anything that you can put dollar signs on, because what you're doing with infrastructure is staying in business. And it takes a peculiar mindset, and fortunately some of us systems level people are pretty demented to actually think that this is interesting and a challenge and worth doing. And it's kind of a food chain effect, because those of us that are closer to the iron understand why this is important. You get higher and higher up into middleware and applications, and it's, what do you mean I have to do some work so this stuff will run on your new platform? It's, and take advantage of it. I've got new features to do. I've got customers crawling down my neck. Why should I do this? So you really need management help if you're trying to do something like this. So I said we designed our own processors, 16-bit. The second generation processor was a long time coming for a variety of reasons, and we didn't get any 32-bit help from the hardware, but we needed some 32-bit virtual address space, so the microcoders and OS people moved something up, which it didn't perform great, but it did the job, because we were already in Linux trouble. I got to work on do the OS work in 1983 when we put real hardware under it, so that was cool. That was much more fun. We built our own through the 80s. The last one we built, we shipped in 89, and it was a really interesting processor. It had things like superscalar elements of certain pairs of instructions would run through the pipeline at the same time. It took forever, it cost a ton. We weren't a big enough company to be continuing to develop our own processors, so we looked around at what our options were, being a big Indian system, and settled on the MIPS microprocessor, and moved over there. And we moved again to the Intel Integrity and started shipping those about 3 years ago. And this year we started taking advantage of multi-core integrity. So how do you take advantage of this? From an API level, as we grew support for 32 bits here and there, we had to have new APIs with 32-bit pointers in them. We built emulators so that you could take your old binary and run it. Basically just do an instruction set conversion on the fly. That didn't perform so well. And so what we did was build what we call accelerators, which basically will read your binary and, insofar as possible, convert it into the new instruction set statically. And so you're maybe not running an optimal version of the new instruction set in terms of what your program is doing, but it's much closer to having native compiled it. And if it gets really in trouble, it'll drop back into the emulator in small spots. this has worked really well. We did this with the MIPS processors. We did it again when we moved to Intel. And we, like everyone else, did our own programming language. It was called TAL. There's still a bunch of TAL code in the world. Kind of at the same level as C, except that you could also go off and write assembly code and work with your stack and so forth. And so when we moved to the MIPS chip, we did what we call PTAL, for portable TAL, which took out some of the machine-dependent stuff. Most of our newer stuff is in C and C++. So the other thing that you get, aside from having to deal with the instruction set, is that you're dragging this anchor with you, and eventually you're dragging a whole set of anchors of the 16-bit instruction set. The peculiarities of how MIPS laid out its virtual address space, the peculiarities of how Intel lays out its virtual address space. The kludges we did to get past 16-bit address space when we didn't have any 32-bit address space whatsoever. And so you find all these artifacts in the code and in everyone's programs that are, because stuff written for our platform tends to be long-lived, this all just kind of drags along with you. The most recent thing we've done, which has been interesting, is to say, chips aren't getting faster much anymore. It used to be you could kind of write Moore's Law on chips, and now the way it's going is that you're adding more cores. And so what we did is kind of a mini SMP thing, which is to say we're going to use 2 chips in a core, but from the point of view of the applications and most of the higher level software we produce, this still looks like one logical processor. That's what we call it. And it's the guts of the system that know that it's really SMP. And the main thing that we've had to deal with in doing that is lock contention, because we've had some pretty big sledgehammer locks in the system, mutual exclusion and so forth, that your SMP performance is going to be less than a uniprocessor because you're spending so much time contending with this stuff. So that's been the latest challenge. System interconnect, we did our own. We really made one change here, aside from doing some high-speed interconnect, which was to, instead of doing a bus-based architecture, do a network-based architecture. This is pictures circa 1997. System scale. This is just an ongoing challenge. Your systems get bigger, your system limits get pushed, you've got more resources to manage, your algorithms break down. And so that's kind of a full employment act for system programmers. And we ran into this big time in the operating system because we said, 256 processes per CPU, that's a huge number. I could put that in 8 bits. This is in the kbyte view of the world. And I will export the fact that it's in 8 bits through all the user APIs. And furthermore, I will export data structures through the APIs and say the process name is here, the network node number is here, and here's the 8 bits with the process ID, and here's the 4 bits with the CPU, and you can see what kind of trouble that gets you in. So I was the lucky dog who got to fix this. And part of this was really trying to do it in a no-gain, no-pain way, where if you're a customer and you didn't need the new limits to no-gain, no limits, you didn't have to do anything. Hopefully you didn't have to do anything if you needed the new limits as well, but really, put the pain on the people that need whatever it is. And we started out with 2 technical dictators and eventually wound up with 1 technical dictator. I said we exposed way too much data structure We didn't version much of anything. We used everything from 0 to 255 as a valid process ID, so there wasn't even anything that we could jam in there to say, don't believe this, it didn't fit, so we had to go back and reclaim 255 to do that. And we hard-coded a bunch of stuff. It was another shortcut we like. So we wound up really sitting back and thinking what we wanted the whole messaging protocol to look like in terms of message contents and message headers and so forth, and put a whole bunch of structure on that. Stop putting internal stuff through the APIs and telling users how to get it and so forth. Lessons for us: compatibility and migration. Basic rule is, if you don't need it, you shouldn't have to do anything. If you're introducing something new, it shouldn't be the default if it's going to make anyone have to do anything different in their applications or system operations or whatever. And right now, a big chunk of my day job is kind of queen of compatibility and migration. When people want to do stuff like this, they have to come talk to me about why they want to do it, why it's okay to do it, and I go consult with the other architects and we go say okay, or don't do it, or don't do it this way, but do it that way. So that's a career by itself. Do design for consistency, do try to keep architectural cohesion in what you're doing with your programs. So it's been a hell of a ride. Going from startup to giant company, and it was hard, and we had a lot of fun. We worked hard, we partied hard. Tandem didn't pioneer the beer bust on Friday afternoons, but we institutionalized it. Every Friday you go down to the cafeteria, and everyone from the shipping clerk to the president would be in there drinking beer and catching up. And got a ton of work done aside from the socializing. And the other really neat thing that Tandem did was the notion of sabbatical, which was that every 4 years we got 6 weeks off. And it actually gave you enough time to go decompress, maybe go do something interesting that was way different than what you did in your work life. And unfortunately, like a lot of other things, that's kind of gone by the wayside as we've merged and gotten bigger. It was interesting times, no question about it. My take is a startup is something you ought to do once. You may find that it's not where you want to be in the long run, but it's just a really interesting experience because you get to do much more breadth of stuff than you get to do in a big company in most cases. I didn't think it was lucky at the time, but I was in a lucky position. I maintained the entire operating system single-handedly for about 1.5 years, and so I still know where all the bodies are buried. And just, got to look at a bunch of how different people did things, got to look at how things work, different ways to do things. And so I do recommend giving it a try somewhere in your travels. Questions? We're supposed to get out of here soon. Yeah.
I'm interested in how you evolved. You probably don't use a bus anymore for your Diamond Connect.
Yeah, we don't use a bus anymore. What we built and shipped about 10, 11 years ago is what we call ServerNet. And if you look at InfiniBand, you'll see a lot of ServerNet DNA in there. We were very much involved in the definition of InfiniBand. But moving to a network approach meant that you got more bandwidth when you scaled up, which you didn't get with the buses.
The other thing was, you talked about, now you've gone to multiple core processors. How does the operating system, you must have fixed the operating system so it would treat the 2 cores as not independent failures, but possibly dependent failures.
Yeah, it's a unit of failure. If something gets hosted in one, the whole thing goes, the whole logical processor goes down.
Yeah, just when you assign processes to processors, you must have to take that into account.
Yeah. Yeah, I mean, there's a whole art to load balancing and where you put what, and we've tried to build some middleware to help customers have that happen for them without them having to think about it a whole lot. It does matter.